In this episode, I'm pleased to bring you a conversation with Dr. Vlad Kindratenko and Dr. Eliu Huerta from the Center for Artificial Intelligence Innovation at the University of Illinois, Urbana-Champaign. Let's start our conversation off with some brief introductions so our listeners have a little bit of understanding of your respective backgrounds and expertise. Vlad, why don't you go first?
Yeah, so I'm a senior research scientist at the National Center for Supercomputing Applications at the University of Illinois, where I lead Innovative Systems Lab and also co-lead the Center for AI Innovation that just recently started. And so my role is to look at new technologies and to try to understand how these new technologies are applicable to current NCSA needs and to future NCSA needs, and try to bring these technologies for our users. I'm also a faculty in the Electrical and Computer Engineering department, where I teach computer engineering courses, and also a research faculty in the computer science department, where I also work with other faculties on AI-related research topics.
Thank you, Vlad. And Dr. Eliu?
I am also co-leading the Center for AI Innovation with Vlad. Before starting this project of getting together expertise across campus to do AI, I was also leading the Gravity Group, which is a group of researchers that focuses on applications of physics and astronomy and cosmology. And it just happens that research in these areas is quite topical in AI. We started some of the early applications for big data in physics, and it just naturally led to the creation of this center. As Vlad says, he's been working for some time on innovative applications of hardware and software for artificial intelligence. And it just happens that we crossed paths at the National Center for Supercomputing Applications. And it was just a natural connection, how the expertise that he has in his team could be combined with applications in big data research.
That's so interesting. And that's a perfect lead into what I was going to ask next is, so for our listeners who may not be familiar with the National Center for Supercomputing Applications, what is the NCSA and how does it relate to the Center for Artificial Intelligence and Innovation?
Yeah, so NCSA was formed in mid-80s or in the second half of 80s in the response of having a shortage or not having access to high-performance computing resources by the US academic research community. It was formed by Larry Smarr by writing a proposal to the unsolicited proposal to the National Science Foundation to form a center like that. That proposal was so successful that, in fact, 4 different centers emerged from it. And NCSA was one of them. And so ever since mid-80s or so, NCSA has been providing high-performance computing cycles to the national computational science community, as well as all the services which are needed to utilize them. But actually, very quickly, NCSA became much more than that. It sort of became a place where not only services are provided, but also where science is done, and where a lot of creative people come together to come up with innovative applications of high-performance computing, ranging from your traditional hardcore science domains all the way to industrial applications and applications that kind of probe the future with high-performance computing. And so for the past many years, NCSA has been running largest NSF-sponsored or NSF-funded high-performance computing resources in the country. The Blue Water supercomputer, for example, and before that, a series of other high-performance computing systems. And hopefully in the future, NCSA will continue to provide the same type of resources to the national computational science community, and as well as the university researchers as well. Now, Eliu, maybe you can say something about the connection to the Center for AI Innovation.
Sure. So also going back to the time that Vlad was referring to, when Larry Smarr decided to have supercomputing research in the US, one of the main motivators for this was that he was also a physicist, and he was interested in solving Einstein's equations. And to do that, since these equations are very complex, he needed supercomputers. And so he had to go to Germany every summer to get access to these supercomputer resources. And it just happens that at the time, Larry Smarr recruited Ed Seidel, who was also director of NCSA since 2014, I think, to 2017. And when he returned to Illinois, it just happens that he recruited me to NCSA to create again a group that would be doing research on this front, which is numerical relativity, gravitational wave astrophysics. And it was perfect timing because it was at the time when detectors in the States were capable finally to see gravitational waves. And so NCSA was part of that story at the level of designing the community softwares that were used to understand these sources. And it just happens that, naturally things evolve. And at NCSA, we are not only content with being leaders with topics that are well established, like high performance computing, or what Vlad is doing, being at the bleeding edge of new technologies for hardware. What we are also trying to do is to find ways to disrupt what is currently in the market, or if you want, in academia. And one of the things that were very topical at the time had to do with how we harness the data revolution for big data research. And I remember having conversations with Vlad about this, and he would be, telling us, well, there is a major difference now between traditional machine learning and deep learning or artificial intelligence. And he had a lab that he was running with, several GPUs. And at the time when we were doing research for LIGO, we realized that some of the tools that he was using, some of the hardware that he had at his disposal, would be great for us to do research. And so with my team, we started thinking about how to innovate on this front. And in 2016, late 2016, when LIGO finally announced the discovery of gravitational waves, we decided to go and apply AI to try to do gravitational wave data analysis, which is something that requires low latency analysis of data. It is not a lot of data, but it is very fast. They call it high-speed data. And so we realized that AI could make a major difference in the way we are doing this type of analysis. And it was a great combination of these are the needs that we are doing. We are at the forefront of research, but it just happens that NCSA is a very unique place. It is not your typical astronomy or computer science or physics department, because you have people from all different areas working in the same building, and they tend to interact a lot. And it was great that Vlad was in the building, that we got to talk to him, and then we became aware of these new technologies, and then everything happens after that.
That is really fascinating. It sounds almost, it's very like cinematic or something, bringing all of these different interests and expertise together. So now let's maybe dig into, you had already hinted at some of the expertise and some of the things that are going on in the building. We got astrophysics, we got agriculture, there's all kinds of industry relationships. So maybe just because I find it so fascinating, let's start with the astrophysics. Ilya, you mentioned the gravitational waves. So could you run us through what does that look like? How is this sausage made in the sense of, you have these hard problems, you have a lot of information. How do you use this technology to solve these problems?
Okay, so let me explain to you the traditional approach, how this is done. So with numerical relativity, which is solving Einstein's equations, you solve these complex equations and then you get some information out of them, which is time series. You can imagine music. You get some time series that tells you what is the signature of the collision of two black holes, for example, or two neutron stars. Then you solve these equations multiple times for different scenarios. Maybe the two black holes have equal masses, maybe they are rotating, or maybe one of the black holes is heavier than the other. And so you get a catalog of all these different signatures, or songs if you want. And then traditionally, what people do is they create a model so that it can produce very rapidly all these different signatures. Now, you are no longer using numerical relativity because it takes several weeks to just complete a simulation of two black holes colliding. So you now have a big catalog of different signatures. And so traditionally, what people would do in LIGO is you get the data from the detector, and then you try to match the data with all these catalogs. So if for example, you assume that you have about 500,000 of these model signatures, then you would have to do matching or template matching between a second of data, for example, and all these different 500,000 signals. As you can imagine, that is super time consuming, and you require dedicated computational resources to do this analysis in real time. Because it just happens that if you have two neutron stars and they collide, they also emit light. And so you want to tell your friends that are managing a telescope, your astronomy colleagues, that they need to go and look at a certain spot in the sky because they are going to see light in a few seconds. So all of this has to happen fast. And so what we thought was the following. What if, instead of having these very complex analysis, you go and learn all these features, these model waveforms or songs, in a hierarchical manner? And what algorithm can do that? Well, neural networks. There you have AI. And so what we did was to take one of these big catalogs that has millions of model signals. And then we applied a lot of very novel techniques that were not available in the literature. So we started, for example, to develop things like curriculum learning that was common in image analysis. But we now did this for time series. So you start with songs that are very loud, and then you gradually reduce the loudness until you cannot hear them. Or you place them anywhere in the data stream because gravitational waves can be anywhere, and you cannot predict when you're going to find them. So after incorporating these new ideas, we ended up with a neural network that is just a few megabytes in size. So you no longer need a supercomputer to go and find gravitational waves. You can use your phone. And so you can go and place this app or executable and then go analyze LIGO data in real time. You no longer need these dedicated resources. And it was revolutionary. People thought at first, well, this is not possible. This is a joke. I mean, we have been doing this for decades. Now you come and tell us that with this tiny executable, you can do the same thing. I don't believe you. And it was, a sociological issue at the beginning. But it just happens that after now 3 years, everybody around the planet is trying to do this. And when I am invited to go and review proposals from people in Asia or in Europe, they are talking about this as, this is great. Everybody should be doing this now. But all of this started in NCSA. It was a very beautiful idea. And we started with gravitational waves, but now we are doing this for a great portfolio of other applications, like, for example, cosmology. We are also trying to combine what we do at NCSA, like scientific visualization, to understand how neural nets abstract knowledge and then make predictions so that we can trust in these algorithms when we use them for other more difficult making decision processes, like, for example, cybersecurity or applications to medicine. So everything has evolved very rapidly, from things related to time series analysis to, for example, industry applications, to big missions that we have at NCSA, like electromagnetic surveys, to other applications like, Vlad can tell you about this, how we study turbulence. So we have developed very rapidly a very diverse portfolio of applications. And one of the big things that we are doing as well is how we go about doing AI at a scale. I think we'll talk about that in a few minutes.
That's so fascinating, and it's really enlightening to hear a story about how, these sort of rare high performance computing, supercomputing solution can be used to then create software tool that then lowers the bar and makes the technology and the process so much more accessible to everybody. That's a fascinating story to hear, and I think it really goes to show why it's important for us to invest in things that seem like abstract science, or it's like, what does this have to do with what's going on? But so much comes out of it. Vlad, he had mentioned the turbulence notion. Could you tell us about that?
Yeah, so we have a project in the Center for AI Innovation where we are looking at how computational fluid dynamics simulations, which are very complex simulations, very time-consuming simulations, can be improved with the use of AI-inspired tools. And there are actually several sort of approaches to this and several useful techniques that AI can bring to this. so CFD computations are very time consuming, and there is a lot of them that need to be run to design, any sort of a modern piece of machinery, particularly if these are things like aircrafts, where you have to understand the dynamics of the entire body. And so AI tools can be very instrumental in sort of improving performance of this, because what becomes possible now is that some of the parts of the computations can be replaced with just AI predictions or models that can be trained on some experimental data or some even simulation data. And then instead of recomputing these results time and time, we can simply predict them using these neural networks. Another interesting development is that we can now also build neural networks where physics actually becomes an integral part of the process behind driving what the neural network is computing. So we can build this physics-inspired neural network models that actually embed some of the features of physics that drives that governs the process, now can be used to generate the results much faster. So, and then the other use of deep neural networks or in the CFD simulations is that certainly now it becomes possible to solve problems which have not been solvable before, because we can now run much larger number of simulations. We can also run much larger simulations, and we can also do an analysis of the entire space, of solution space, to try to find specific solutions to specific problems. And so this actually turned out to be a very interesting development that is of great interest to industrial partners at NCSA, that many of them are using CFD simulations as sort of a vehicle to develop new machinery, new tools, and new products.
I'm curious to hear how you work together with industry. What does a relationship like that look like?
In early days at NCSA, it was recognized that having access to a supercomputer also enables something that industry could benefit greatly from. And NCSA Industrial Partners Program was established, also in early days at NCSA in 90s. And this Industrial Partners Program continues to exist. It's called in NCSA Industries these days. The purpose of this program is to basically provide access to the latest and greatest both technology and solutions that have been developed at NCSA to our industrial partners, and make them being able to make use of this technology for different purposes. In fact, I actually came to NCSA as a postdoc working on a project sponsored by Caterpillar to build a virtual reality that at that time in the mid-90s actually required a supercomputer to render the 3D scenery. And this technology was eventually picked up by Caterpillar, and they built virtual reality setups in their own facilities and continue to use it. And we kind of see, and so this at that time it was sort of a revolutionary technology that gave an advantage to companies who had access to it. And so today we see exactly the same developments with AI. Companies who can figure out how to make use of AI capabilities, they have essentially a technological advantage over other places, other companies, because they can solve their problems much faster and get to their products much faster, and deliver new products and services to the community. And so NCSA industry program has been sort of instrumental in enabling these companies to take advantage of these latest developments.
I wanted to ask you specifically about the amusingly named HAL supercomputer program that you have there and how it uses the Power 9 cluster.
Yeah, so some number of years ago, 3 years ago or so, we actually looked at the research community on campus and asked this question: what do you use today to run your deep learning models? And the answer, amazingly, the answer was that majority of the researchers had a small GPU system somewhere there under their desk and just use that. And with that, they were not able to achieve all the potential of deep learning. They were limited in the amount of computations they can do, in the amount of, in the size of the models they can run, and so on. And so we asked this question, but so what would be a useful resource such that all of the faculty on campus can make use of and can advance their state-of-the-art in their research fields using deep learning? And so we came up with this idea to build a computer system that would be shared resource for everybody on campus and can help them. And there was actually a program at the National Science Foundation called MRI, Major Research Instrumentation Program, that was designed to fund building research instruments that can be shared resources for campus communities. So we applied for this research instrument grant. In order to apply for it, we actually had to come up with an idea how our system will look like. And so we've done some research. We look at it, what sort of technology is out there, and especially what sort of technology is going to be available, say, in half a year or in a year from that point, because it takes some time to get funded. And we realized that the upcoming technology that is going to sort of bring the next level of advancement is going to be IBM Power 9 system. And this is actually the same technology that's been developed by IBM for these other supercomputing centers in DOD and DOE domain. And so we decided that we will be building our cluster using that technology because that was state of the art, something that was providing capabilities that no other technology would provide that capabilities. So we worked with IBM to come up with a proposal with a system that could provide these capabilities and submitted this proposal to the National Science Foundation. And we actually got funded. And so we built this system that became operational about a year and a half ago called HAL, which stands for Hardware Accelerated Learning Cluster, but we for short HAL. And this is actually a 16-node IBM Power 9 cluster that embeds the latest IBM microprocessor technology, latest GPU technology, or it was latest up until this summer when NVIDIA announced the next generation of the GPUs, and also latest interconnect technology. And so this cluster was built to support a variety of deep learning applications. And so for that, we use IBM software stack developed specifically to provide support for the TensorFlow and PyTorch and Caffe frameworks, including distributed deep learning, so the ability to run this learning across multiple GPU nodes. And so now this cluster became sort of the centerpiece of many of the research activities on campus that utilize deep learning as their technology of choice. We have well over 300 users on the system. These users are running jobs constantly, using anywhere from one GPU to many nodes with GPUs. We've done our own benchmarks where we can sort of train ResNet 50 on ImageNet in just under an hour on this cluster. Something that used to take in the early days when this network and this data set were just developed, it would take many days to train it. On this system, we can train it in a very short period of time. And so now we support actually a very large number of users on this system that actually go and do their science. So they are no longer concerned with availability of the resources or with the availability of software or the ability to run something with large data sets. They're only concerned about how to advance their science. This cluster provides the platform for that. Maybe Eli can say something about the use of this cluster in his group as well.
Yes, so there are 3 examples. One is related to electromagnetic surveys, and this is, for example, people that have telescopes and they want to study galaxies. And NCSA led one of the most ambitious projects on this that is called the Dark Energy Survey. So they were able to capture about 300 million galaxies. And galaxies have different shapes, and they tell you a lot about how they form. If you look at an elliptical galaxy, you know that it is an old galaxy. If you look at something that looks like spiral, that's a young galaxy where stars are being formed. And so it just happens that astronomers want to see what they are looking at. They want to understand it. And what they do is they tend to classify them according to their morphology, elliptical, spiral. Now the problem with this survey is that 300 million galaxies, you're not going to use your students to classify them by hand. That is going to be super painful and it will take a lot of time. And so we use HAL to develop a method that is automated, which is now using neural networks to do this type of analysis. And the beauty of this is that we combine information that we obtain from Citizen Science Campaign, the Galaxy Zoo project. So we train neural networks with this information from a different survey. And now with HAL, we train a neural net in just 2.1 minutes using the entire cluster. usually if you only use one Volta GPU, it would take you about 2.5 hours. But with the entire system, you can finish that in minutes. Now, what is the beauty of that? Well, the beauty of that is that by training these models so fast, we were able to understand how the neural net was classifying the galaxies. And it just happens that this way of solving the problem was so appealing that the Department of Energy that funded us to do this research featured this as a highlight. And not only that, we were also selected to go to the visualization challenge in supercomputing 19. And this visualization was selected as one of the 6 semifinalists there. And just to put the cherry on top of the cake, this was also featured in the I Am AI GTC keynote in May. So HAL was at the core of all these developments. We had the computational resources, the ability to do this type of work, because we go and talk with Vlad and we tell him, we need to use the cluster for a couple of hours on a given day. How do we go about this? How do we make sure that we are using the latest technology from IBM, from NVIDIA, so that we can produce top class research? So that is one example. Another one has to do with how we use HAL that has 64 GPUs to try to run some of the grand challenges in supercomputers like Summit, which is a larger scale version of HAL. And so we used HAL to train a neural net that is able to measure how fast black holes are spinning. Now, this is a very complex problem. We need millions of these model signals, as I explained before, to try to understand the parameter space. Now, it just happens that this neural net is so complex that using just one GPU would take us about a month to train it. With HAL, we reduced the time to insight to just 12 hours. So that is amazing. But then we asked the question, what if we use the knowledge that we have from HAL, which is related to all these different hyperparameters or knobs that you tune to train the net, and we want to do this in Summit? And so with the parameters that we identified in HAL, we went ahead and tried to train this same model in Summit using over 6,000 GPUs. Minimal changes. Almost all the hyperparameters work off the shelf. And in just 1 hour, we had the same model, same accuracy, full convergence, etc. So HAL in this way is serving as the bridge to go into bigger platforms. And this is not trivial. People have developed software stacks to try to do this, identifying the hyperparameters. But it just happens that the configuration in whole is so good that whatever information you get out of the system, you can go and almost transplant these into larger scale systems. I haven't heard of any other application that has this type of capability. So it is great.
That's really interesting. And it reminds me, it's a similar pattern to what you were mentioning before, how, from the systems you have there, you've been able to now you can do processing on an iPhone and find gravitational waves. And the same thing, because I'm imagining, getting time on a system like Summit is probably difficult to do. And there's a lot of scheduling. So it's like, if you can figure out your system on something you have, and then when you get time there, now you can be really effective versus trying to hash it out and figure out what you're doing then.
That's right. And it just happens that to get time in Summit, we had to come up with preliminary results. And what we use as preliminary results is the runs that we had using the entire cluster in NCSA. So, that opened the door as well to get access to those resources.
What do you see in the future for HAL and for the AI Center of Excellence that you can't do today that you wish you could do with those assets to support your industry partners?
Yeah, so with regards to HAL, the system is big, but not big enough. So we would really like to see the system to grow and have more and more computing power in it, so we can try to solve much larger problems that we can solve today. So that's one dimension in which we're interested. Another dimension, we're also interested in using sort of more interesting architectural modifications to the system. In particular, things like field programmable gate arrays or FPGAs that can enable a new breed of applications. particularly for inference applications, where you have the trained model, but now you just have to run this model against very large data sets that you have to classify or sort somehow or filter somehow. So we are working on that as well. So we have a project where we are building bits and pieces of the inference pipeline that will enable us to run complex neural networks on FPGAs and then link it together with sort of the traditional frameworks such as PyTorch, for example, to enable others to seamlessly use the FPGAs underneath. So this is another direction. I think, and the development of user interfaces and sort of ability to make an easy use of this technology for people who are not computer scientists by training. So for that, we've been developing these interfaces. You can just connect the whole cluster through the web browser, and you can launch a Jupyter notebook, because this is, for example, a typical traditional approach, how a lot of people are starting to develop models at first. So now we have this technology in place where you don't need to know anything about file systems and a secure shell login into the system. You just use web browser and you have your traditional notebook. We also are looking at other tools that enable to use existing models. So we actually have a couple of tools on HAL which are currently supported, but we are looking at enabling more of these tools. One of them is H2O, which is essentially a collection of machine learning tools, including some of the neural networks that enables to simply provide model parameters through the web browser and then enable training or enable that model to perform some computations or some data set. Another one is IBM Visual Insights, which is also web browser-based software package for running complex deep learning models. And so this IBM Visual Insights in particular interesting because there are very few models developed in it, like a handful of models, but those are models which are frequently used to solve whole classes of problems. And so now it's possible for somebody who has no training whatsoever in computer science, but understands how deep learning works in general. Well, now it becomes possible for him just to load his data sets into this tool, and with a few clicks of mouse to start training on the data set and get some results. We actually just recently, we've done an interesting study where we took one of the data sets which are available online with the COVID X-ray, chest X-ray data set. And we were able to put this data set, upload this data set into this Power IBM Insights tool, and we were able to train the model very quickly, and that model actually was pretty selective in recognizing COVID versus non-COVID images, X-ray images. So we are looking forward to sort of having more tools of this nature and then enhancing existing tools that will enable users of HAL to use the system without actually knowing much about underlying hardware or underlying technologies that runs there. Just the domain specialists should be able to use it to solve their problems. So this is another big direction in which we are looking for in supporting HAL.
So let me ask you this. Is there anything I didn't ask you that I should have, or is there any closing thoughts?
You know, one other thing that we have learned, and I'm sure Vlad can tell you many stories about this, is we will only know where to go, where the challenges are, when you make this technology accessible to students. And I'm talking about students in particular, because it just happens that some of the major disruptive developments from NCSA came from students, like Mosaic, the work that we have been doing with AI. It is because we provide access to these resources to students that are, you know, very bold. They are eager to go and try new things. And they are the ones who tell you, you know, the system is great, but we really need the following to go and address this problem. And so it is difficult to predict where the technology is going to be a few years from now. But we can only say that it will continue to move in the right direction when these innovative minds get access to their resources. And so using HAL as one of the pillars for the training program that is imparted by the center is essential. And that is why we emphasize this specific aspect. One of the thrusts of the center is to go and democratize access to deep learning training. And this is what Vlad and I have been doing over the last year, providing access to all sorts of students to these resources. And they show you with just access to these resources, for example, through hackathons in a couple of days, They come up with some really innovative solutions to big problems that, faculty members who suggest the problems, they think this is going to be impossible to solve in 2 days. And then suddenly these students come up with some really great solutions. So I think this is the way forward. We continue to provide access to students and give them an idea about what they can go and try with these technologies.
That's a really heartening message. And I love that it's based on things that you could get a hold of today. Like if you learn some, basic Python and Jupyter notebooks, now you're in a position that when you get to college or you have access, you could actually make use of these sophisticated systems.
Yeah, that's right. And so we've been actually providing training sessions for students to learn how to use the system, how to get onto the system, how to use basic tools, and also how to build basic models and train these models. And as Eliu was saying, this is actually quite refreshing to see the students come up with such a unique and such an interesting and powerful solutions using this technology once they realize that how much power they have in their hands with this system.